Hey everyone, and welcome. Today, we are diving into a really powerful tool from the calculus toolbox. It's called the comparison test. And honestly, it's a total lifesaver for when you bump into those integrals that just seem absolutely impossible to solve directly. By the end of this, you're going to see exactly what I mean. So picture this. Your professor slaps this integral on the board, e to the power of negative x squared. You try everything you know, use substitution, integration by parts, and nothing. It just doesn't work. And that's because this function, which is actually super famous in statistics, doesn't have a nice, simple antiderivative. So what do? Are you just stuck? Well, not exactly. We just need to ask a different question. Instead of asking what's the exact area, we ask, is the area finite? And that question leads us straight to the core idea of comparison. You know, in fields like physics or engineering, it's often way more important to know if a system is stable, if the total energy converges to a single number, than it is to know the exact value of that number. The comparison test gives us a way to figure that out by focusing on how a function behaves in the long run without ever having to solve the original integral. And the logic behind all this? It's actually incredibly simple. Just think about it. On the left, if you've got some big function and you know its total area is finite, it converges. Then any smaller function that's always trapped underneath it, well, its area has to be finite too. It's got nowhere else to go. And on the right, it's the same idea. If your small function's area blows up to infinity, and your function is always bigger than that one, well, yours has no choice but to go to infinity too. Okay, so this simple, intuitive logic gives us our first official tool. It's called the direct comparison test, and it is pretty much exactly what it sounds like. A direct, head-to-head comparison between two functions. So for these rules to work, you basically need two things. First, you need a comparison integral, we'll call it g of x, that you already know the answer to. This is usually going to be a p integral, 1 over x to the p, which we know converges as long as p is bigger than 1. Second, and this is the important part, you have to prove that one function is always bigger than or equal to the other. If you can check both of those boxes, you're good to go. All right, let's see this thing in action. We've got the integral of 1 over x squared plus 5. Now that plus 5 in the denominator, that's what makes it a pain to integrate directly. But it looks an awful lot like a function we do know how to handle. So let's compare it to good old 1 over x squared. Step 1 is the inequality. Since x squared plus 5 has a bigger denominator than just x squared, the whole fraction has to be smaller, right? Bigger denominator, smaller number. So the inequality holds. For step 2, we check our comparison function. The integral of 1 over x squared is a p integral where p is 2. And since 2 is greater than 1, we know for a fact that this integral converges. And there you have it. Our function is smaller than a function whose area we know is finite. It's pinned down. Therefore, our original function's area must also be finite. It converges. The logic is just airtight. Okay, let's try another one. How about the integral of 1 over x minus 1? Again, that minus 1 makes things a little messy, but the whole thing really feels like 1 over x. Let's run the same play. Step 1, the inequality. This time, since x minus 1 is smaller than x, its reciprocal must be larger. A smaller denominator makes a bigger fraction, so 1 over x minus 1 is greater than 1 over x. For step 2, we check our comparison. The integral of 1 over x is a p integral where p is exactly 1, and we know that any p integral where p is 1 or less diverges. And that's our answer. Our function is bigger than a function that we know for a fact blows up to infinity. It has no ceiling above it, so its area has to be infinite as well. It diverges. Now, the direct comparison test is fantastic when that inequality is super obvious. But what happens when it's not? What if you had something like 1 over x squared minus 5? Suddenly, the inequality flips and our whole convergence test falls apart. This is a super common problem, and it's exactly why we need another tool in our belt. And this brings us to our second, and honestly, often much easier tool, the limit comparison test. This one is incredibly powerful because it lets us sidestep that whole tricky inequality proof. So here's how this one works. Instead of comparing sizes, we compare their long-term behavior. You take your function f of x and divide it by a comparison function, g of x, and then you take the limit as x flies off to infinity. If the answer you get, L, is a positive, finite number, not 0, not infinity, it means the two functions are basically growing at the same rate. And if that's true, their integrals have to do the same thing. They're either both going to converge or they're both going to diverge. They're a team. This quote from Baker's math class really just hits the nail on the head. You're not getting bogged down trying to prove one thing is bigger than another. You're just asking a much more elegant question. Do these two functions act kind of the same in the long run? All right, let's take our new tool for a spin. We've got the integral of 1 over 1 plus x squared. Now, we could probably wrestle with direct comparison here, but let's use our new, more powerful method instead. So, step 1, we pick our comparison. The most dominant term in the denominator is that x squared, so let's choose g of x to be 1 over x squared, which we already know converges. Step 2 is to set up the limit of our original function divided by our comparison function. Now, after a little bit of algebra, flipping that bottom fraction and multiplying, we get the limit of x squared over 1 plus x squared. As x goes to infinity, this limit is just 1. And that is our key. Because our limit, L, is 1, which is a finite positive number, the test tells us that our integral does the exact same thing as our comparison integral. Since we know the integral of 1 over x squared converges, our original integral has to converge too. And look at that. No messy inequality proof needed. So much cleaner. So now you've got two fantastic tools. The final piece of the puzzle, the real art of this, is knowing which one to use and when. Think of this slide as your cheat sheet. Use the direct comparison test when the inequality is simple. It's obvious, like when you're just adding a number in the denominator. But when that inequality is tricky or just not clear at all, reach for the limit comparison test. If the two functions kind of look like they have the same long-term behavior, the limit test is almost always the faster and cleaner way to get the answer. And that's really what the comparison test is all about. It's not about finding a number, it's about understanding behavior. It's an incredibly powerful way to prove that an area is finite even when you literally can't calculate its exact value. So the next time you see an integral that looks impossible, don't give up. Just ask yourself, what does this behave like, and which tool can I use to prove it?